Good afternoon. I'm here to tell you about Sayid, a debugging and profiling tool that I wrote for Clojure. All right, a bit about myself. My name is Piel. I was born, raised, and I'm living in the Philadelphia area. I've been programming for a while, professionally for the last 15 years or so, doing Clojure for about 4 now. I'm working in the analytics division of Magento via a very recent acquisition of my previous employer, RJ Metrics. And my face looks like that. Before I tell you anything else about Sayid, I want to emphasize the hugeness of the impact that it's had on my life. It's probably less than, say, like having kids, but more than getting a pet, like a dog or a fish or something like that. Because I write Clojure almost every day, and every one of those days I am using Sayid, so it's become an indispensable tool for me. For the better, yeah. All right. So what was the problem? Why did I feel the need for Sayid? Well, I do love Clojure a lot, like a lot. I think its interactive development style does a lot to ease the debugging process, but I was still left unsatisfied by some things. Especially, I think, a very prevalent debugging practice that I like to call code sprinkling. Many times after an intense bug hunt, I would step back and look at my code and see what I had done to it, and it was disturbing. There'd be print lines and defs all over the place, sometimes like real wacky things stuck into threading macro expressions to try to figure out what's going on in there. I felt like I was doing something wrong, and if you are not doing something like this and you do like what you're doing, drop me a line, because I want to know what people are doing out there to solve this kind of thing. Another tool that you might be using is a step-through debugger. Cider has one, I think Cursive has one, and maybe that's the gold standard of debugging. Not for me, at least. There's something different that I wanted. All right, so it was about a year ago that I decided it was time for action. And I started writing the first lines of code of what eventually became Sayid. Now, here's my big pitch. Sayid can largely replace these other tools and techniques that I've described. I hardly ever sprinkle anymore, and I hope to sprinkle even less in the future. All right, so when I got started, I had some questions that I wanted to ask myself, like, what am I trying to do? And has it been done before? And does it have a name? I did some research, and there were some relevant terms, things like reverse debugger, historical debugger, even time-traveling debugger. But my favorite, of course, was omniscient debugger. Omniscient debugging is debugging with full knowledge of what's going on in your code, like all the function calls, all the arguments, all the return values, all that stuff. That is what I wanted. And like, has it been done before? Of course, everything's been done before. But it didn't seem like it was being done very often. So I turned to Google to see what was going on out there. So here's a chart showing 3 different search terms in the Google search frequency. First, in blue, is the omniscient debugger, which had a little bit of activity in 2004, and it's just been dropping off since then. Today, I think it's like me and 3 other people that look for it. Next, I have IntelliTrace, which seems like it was the most recent kind of major product offering in this area. It was a feature that Microsoft included in Visual Studio 2010. And you can see there was a spike of activity back then, but interest there also kind of dropped off quickly. And searches for Rich Hickey are about to outpace it right around now. So go Rich. But despite the apparent lack of popularity of omniscient debugging, I decided to press on and see if I was crazy or just severely misguided. There was one tool I wanted to mention that I discovered along the way is Clojure Tools Trace by Stuart Sierra. Clojure Tools Trace is pretty cool. It captures execution activity at the Omniscient level and then prints it out kind of like a log. So like the core technical like idea was there, but I saw a lot more potential. Anyway, the first lines of code that I wrote for Sayid were completely inspired by Clojure tools trace. So thanks, Stuart. All right, so that's the background. I have developed a highly contrived example application for demonstration purposes. It's pretty simple. It relies on some libraries like Composure and Liberator to expose simple HTTP API. And I'm going to use it to demonstrate like 2 different contexts that you can use Sayid through. One is executing your code through a test, and the other is executing it through an HTTP request, and I'll be using curl for that. The book Clojure for the Brave and True uses a hot dog vending machine as an example in one of its chapters. I like that model a lot because vending machines are just complex enough that they're interesting, and most people know how a vending machine is supposed to work. But I wanted to be a little bit original, so I went with a taco vending machine. So that's the example application we'll be looking at. All right, so I was very concerned that I was going to get up here and forget what I was trying to do. So I put together this demo checklist for us. All right. We are going to look at all these things. We're going to look at how to get set up to use Sayid briefly, tracing a namespace with Sayid. We'll execute a test. We'll view and query the resulting trace tree that we've captured. We're going to look at the magical, although a little bit buggy, inner trace feature. Then we're going to debug. We're probably going to fix a bug, I think. I'll switch over to using curl, and then we'll look at Sayid's pretty print buffer feature, do a little bit more debugging, and finally we'll track down some slow code using Sayid's profiler. All right. It's harder to type in front of hundreds of people. All right, so if you use Line, you're probably familiar with profiles.clj, or you might be, I don't know. This is mine. It's pretty light, doesn't have a lot going on. The important thing is that I have 2 plugins. One is Sayid nREPL, which Sayid relies upon, and the other is Sayid itself. The plugin is doing 2 things. First, it's injecting a dependency on the Sayid library itself, which is critical. And second, it's injecting the nREPL middleware, which is necessary if you're using the Emacs integration, which is what I'm going to be demonstrating. Although technically, you can use Sayid completely just from the REPL, which means you wouldn't need the middleware in that case. So, all right, so here's our test. This is the initial state of our taco vending machine. We've got tacos. We've got 10 tacos loaded in here. They cost 85 cents each. And we can go down here. All right, go down here, and here is our test. We take our test vending machine, and we're going to insert a series of coins. We got a quarter, dime, nickel, and penny, totaling to 41 cents. Then we press the taco button. Now, when you insert 41 cents and press the taco button, and tacos cost 85 cents, you should not expect a taco. But let's see what happens. But before I run the test, I don't want to forget the thing that I always forget to do when I'm practicing this, which is to use Sayid to trace the namespaces. So here, yeah, you can see the bottom, right? We're using like a wildcard, and we're just tracing all of the namespaces in our contrived example application. All right. So when I trace these namespaces, Sayid pops up a nice little buffer for us, which details all the namespaces that have been traced, as well as the number of function vars in each one that have been traced. And you can even like drill in and see like, okay, here's all the functions in that namespace, and just feel pretty good about the situation. All right, so we got the traces in place. Let's run this test. Oh, test failed. That's too bad. I wonder what happened. It might be a bug. Yep, didn't see that coming. There's a bug in this code, but yeah, what's the bug? Oh, we got back a taco, which we didn't want, and also we got some change, 2 quarters and a nickel. So yeah, that's a bug, but that's okay because we have a great debugger at our disposal. All right, so did Sayid do anything for us at this point? Yes. Here we go. All right, what is this thing? I'll tell you. This is everything that Sayid captured. This is the trace tree as visualized by Sayid. I'm going to zoom out real quick, just show you that it's big. It's not that big, but it's big enough. Go big. All right, and each node in this trace tree represents a call to a function. And we're looking at a summary view. So each node is just showing the name of the function. But in fact, we do have more detail. So I can drill into just the call to press button and see here, press button was called with 2 arguments. They're machine and button. And you've got the values that were passed in, nicely pretty printed out for us. And finally, also the return value. And you can see the return value here has the 2 quarters, the nickel, the taco, which agrees with the bad test results we got before. All right, so, oh yeah, the colors and indenting, right? That's how Sayid represents kind of like the hierarchy of the tree. So press button, for example, made a call to valid selection called get selection, and you can kind of see how like that's nested. All right, so now we're going to do, let's try to debug. We made those calls to insert coin. That doesn't look especially interesting, but when we hit press button, all sorts of things happen. So we're going to drill into that. Sayid gives you some capability to query the trace tree, and I'll give you a little bit more detail on that later, but suffice to say, we're going to look at the details for press button and all the function calls that occurred below that. There we go. So yeah, there's press button, which we just saw. It makes a call to valid selection, which makes a call to get selection. Now I'm going to assume a little bit of programmer's intuition and notice that this doesn't seem right. When we call calc coin value, passing in the 4 coins, which we said were worth 41 cents, but it's returning $1.40. That seems like pretty suspicious. So we use Sayid to just jump to that function. And there's the definition of calc coin value. Cool. All right, now check out this feature. Sayid has a feature where it kind of attempts to encapsulate like a given instance of a call to a function. And the way that works is hit a button, takes us back over here, and I'll show you what it's done. It took the arguments that were being passed into calc coin value, stuck them in vars in a var in a special namespace. Like, so if we evaluate coins 1, there's the coins that we'd passed in, and you can eval the whole expression and see $1.40. So this can be pretty useful when you've narrowed it down to the point where you're looking at a specific function and you want to kind of like iterate on it and get the behavior right or something along those lines. So, yep, $1.40. All right. Right, next I was going to show you the inner trace feature, which sometimes breaks, but shouldn't, because this has been very carefully prepared. So the inner trace feature works kind of like the normal trace feature, except instead of being at the function level, it's at the expression level. So it's looking at all the values that are being passed into the expression, and as well as the final value of what the expression itself evaluates to. And we'll turn that on. And again, we get the trace buffer popping up, and we can see like here, there's that the calc coin value function that's now has the special inner trace on it. I'm going to clear our log, and we will run the test again. All right, we still get failure, which we expected, but now should be something different. There we go. So I queried for all the calls to that function. And now I can look at just the one instance here. Now we're looking at what was going on in calc coin value, except now it's at the expression level. So we've got the threading macro returning $1.40. Next we're applying plus, also returns $1.40. And then we finally get into a little bit more detail, something interesting when we make that call to keep coin values coins. And looking through here, we see the value of quarter, dime, nickel, penny. Penny is 1, as in like $1, not 1 cent. So that's looking like it could be a bug. Again, Sayid will just jump us to that line of code. And if we look at coin values here, which is conveniently defined right above the function, yep, there's penny. It's 1. Let's change that to a cent. OK, we did that. Now we can reeval that. All right, this expression is now returning 41 cents, so that's a pretty good sign that we fixed something. We can go back to the test. Yes, test passed. All right, we debugged. I've never gotten applause for debugging before, so I really appreciate that. My boss never does that. All right, cool. All right, so what? Let's review. What did we do? Yeah, we looked at how to get things set up quickly. We traced. We executed. We viewed and queried the trace tree. Inner trace worked. That was good. And then we found a bug, as promised. All right, so let's switch over to curling our application. I'm going to, what am I going to do? I'm going to clear the log, the trace log, start fresh. Oh, no, wait, I know. I got to clear that inner trace as well. I don't want to mess that up. OK. Cleared everything out, retrace all the namespaces. Cool. All right, so here's our curl request. We are hitting the taco endpoint. We're inserting 4 quarters, and again, pressing the taco button. 4 quarters is $1, so now we should get that taco. But we didn't. No acceptable resource available. So that's some kind of crazy HTTP API thing. All right, so this time, what Sayid captured was much less. It got us to, as far as like our liberator resource, we can drill into that, and there is our ring request, which is nice. And we can see we did get a 406, no acceptable resource available. But this actually does not give us a lot to go on. And you might wonder, well, what are our options at this point? Well, I'll tell you, because we have them. Sayid allows you to trace like any namespaces that are available, not just ones that are yours, or like that you have the code to. So what we can do is we can trace in the liberator. And there's our trace buffer again, and we got some liberator namespaces in there. Great. We're all set up. Run curl again. Same response, but this time, hope this works. Yep. All right. I'm going to zoom out real quick. Look how much bigger it is. Liberator does a lot. That's crazy. And we don't want to have to step through all that if we don't need to, and we don't need to. That's great. Sayid has a feature called views, which lets you like configure or customize which data is coming back when you view a trace. So if there's a certain piece of code or library that you're working with on a regular basis, it might benefit you to set up a view. I happen to have set up one for Liberator for us. There we go. And now I can turn that on. And what are we seeing now? All right, now we're just seeing calls to liberator's decide function, which is what we want. And you can see it's just showing us the name of the decision and the return value, which is 4 6s all the way down. So we can step through here and see like how far down the decision tree did we get. We got this far. Last decision that we made was language available. So that's where things went wrong. So now we've got some kind of clue. We can go to our liberator resource and see what was our configuration. Well, we set up languages, and turns out the only available language is Spanish. And if you look at our call request, we only accept English. So this is a Spanish-speaking taco vending machine, and we're trying to speak English to it. Maybe that's the bug. Ta-da! Taco. Muy bien. All right, this is going okay. All right, what else are we going to do? Oh yeah, pretty print buffer. Let's do that. So the pretty print, I'm going to run this again for fun. Oh, this is where I always screw up. Don't do it. One more time. There's an awesome thing that I do sometimes where I accidentally try to dump all the details from the trace, and it's too much, and it locks up the VM for a while, and then I stand here and I'm embarrassed. But I'm not going to do that today. Yes, I didn't do it. OK, so let's go in here again. So this is that same call to the liberator resource, and we're passing in this very large ring request. It's big enough that Sayid has truncated it for us because it doesn't want to, overwhelm us. And when that happens, if you want to get more detail on what was captured, you can go into the pretty print buffer, hit a button. So now we're just looking at that ring request, and see, it's not getting truncated anymore. And this is useful because there's some things like you can navigate through it in kind of like a sane way if you want. Using like navigation keys, you can go like through the levels and siblings and whatnot, parent, child, that whole thing. But my favorite feature is that say you are in a big structure like this, which happens to me a lot in Clojure, and you find some value and you want to know where in the structure is that value exactly. So I've located this third quarter, which I'm interested in, and hit a button. And now at the bottom, you see body insert coins 2. That is the path that you could pass to like get in, for example, to find that third quarter that we were looking for. So that's helped me out a lot of times. Last one. OK, so we pretty printed, we debugged. Profiling. Let's do that. So, OK. The profiler is not integrated with Emacs, so we're going to be using the REPL for that, but that's OK. What am I doing? So I'm calling profile analyze the workspace, which is the trace tree. And then I'm going to zoom out. You might not be able to read this, but at least you get a feel for it. So here's a table. These are all the function calls that were in our trace tree, and it's sorted by a metric that I'm calling net time sum. Net time sum is the metric that I think you actually want to look at when you're doing profiling. And what it is like the net time sum for a function is all the time that was spent in a function minus the time that was spent in calls to other functions that were called. So I think that gives you like the best kind of indication of where time is actually getting spent when you execute your code. And for example here, by far, the biggest net time sum is coming from a function called slowpoke. So that's suspicious already. And let's zoom in. All right, so we look at slowpoke here. Yeah, it's just calling thread sleep 50, which is not efficient. Now, just as an example, try to explain what I was talking about with net time sum. There's another function called questionable. All it does is call slowpoke. So you could imagine that a profiler might say, like, OK, we're spending a lot of time in questionable, but that's not actually interesting to us because all the time being spent in questionable is actually being spent in slowpoke. So Sayid marks slowpoke as the slowpoke. In questionable, it says that's fine. All right. Where are we? Yes. All right. Made it through the checklist. Success. OK. So I showed you how we can query the trace tree before, and I wanted to give just like a little bit more detail on that. Let's pretend that this unrealistically balanced tree is our trace tree. Sayid actually has a really powerful interface for querying this, although only a subset of it has been integrated into Emacs so far. It's a good subset, so that's fine. Two things that you can do are query for all the calls to a function or a specific instance of a call to a function. So for example, here I've highlighted, let's say this is an instance that we're interested in. You can also modify the query to do things like show me that instance plus all of its ancestors, or that instance and all of its descendants, or both. You can further modify it and get and limit the number of generations that you're looking at. So here's that instance of a call and its immediate ancestors and descendants. As I said, you can also get all the calls to a function. So let's pretend that's what this is. And those same modifiers are available to you. So you can do this kind of thing, which is useful sometimes when you're debugging. A lot of what makes Clojure special got leveraged in the making of Sayid. This is a long list. I'm going to go through it in some more detail. Immutability and structural sharing do a lot to improve the memory usage efficiency of Sayid. In another language that relied heavily on mutable objects, it would be necessary to clone everything as it got captured so that you could be sure it hadn't changed when you later went to view or query for it. That would be costly. But with Clojure's immutable values, you can capture them, be pretty sure they're not changing on you. Now, I'm going to attempt to explain my very simple understanding of structural sharing and why I believe it benefits Sayid. Here we got two trees. The yellow one on the left, or the yellow one on the right, and the blue one on the left are the same, except the yellow one has one additional element added to it. Now, these are supposed to represent like values that Sayid has captured. So like persistent data structures like a vector. And the yellow one's got one additional element. And as I understand it, you might represent the memory usage of these two something like this, where the green nodes represent reused nodes or like shared memory. Now you can imagine if when Sayid captures a larger data structure, as it passes through like a series of functions, that there would be many more green nodes, and those savings would really add up. All right. When Sayid traces a function, it finds that function's var, it takes the original function, wraps it up, and then changes the root binding in order to replace that original function. Now, the original function gets stuck on the metadata of the var, which makes it very easy for Sayid to like trace and untrace any given function's var. This is my tricky slide. When a traced function gets called, Sayid looks at a dynamically scoped var for an atom to write trace data to. Now, this map up here in the top left represents like a simplified version of that trace data. We've traced and executed a function called func1. We captured its name. It gets a children atom. And this children atom will have trace data written to it whenever func1 makes calls to other traced functions. So we capture the arguments going into func1. Func1 then makes a call to func2. And this is when we start writing to func1's children atom. Func2 gets its own children atom. We capture its args. We capture its return value. Func1 then makes a call to func3. That same process plays out. Finally, func1 completes, and we capture its return value. So this is how Sayid goes about building its trace tree. I'm going to talk a little bit, just briefly, about the inner trace feature. As I said, it's like a little bit buggy, and it's just kind of nuts. But I'll mention it. The key feature of Clojure that the inner trace feature leverages is the ability to eval source code on the fly. And the reason it does that is, here's a ridiculously simple function, right? So even something as simple as this, when inner trace gets its hands on it, it turns it into this. Now, so yeah, no wonder it's buggy, right? Like, this is crazy. Don't worry about the details, but suffice to say, it generates this source code and evaluates it and replaces the original function. And this is what goes about tracing every single, like the call to every individual expression. All right. Sayid has some limitations and problems. There's a reason why it's still in alpha. Probably the biggest problem is the bigness problem, which is because Sayid allows you to capture so much information, you have to be very careful. You have to give some thought to what you're tracing, which namespaces, and once you have those traces in place, you have to think about what you're executing during that time. Because you can definitely capture enough to just blow up your JVM. Don't use this in production. And even if you do manage to capture all this information, it might be difficult, it might be slow or impossible to view the resulting trace or query it. So, fair warning. Other limitations, the state of dynamic vars and mutables that get referenced by a function, those don't get captured at the time. Multi-methods, like technically they work. The support's a little bit messy. And yeah, finally, as I mentioned, inner trace is not especially reliable. It breaks a lot, especially if your function has a recur in it. That's right out. All right, so what does the future hold? I'm not done with Sayid. Even though I use it every day, it is definitely alpha. And it's really great that Sayid has benefited me so much, but it would be even better if it helped anybody else besides just me. So with that in mind, Sayid is open source under the Apache 2 license. I've got it up on GitHub. PRs and issues are welcome, of course. I'm very interested in getting more editor integrations, especially Vim. All my coworkers use Vim, and they use this as an excuse to not use Sayid, and I want to take that excuse away from them. Now, I'm an Emacs guy. I don't know anything about Vim, so I'm not going to write this plugin myself, but if somebody else is interested in doing it, I would provide whatever kind of support or documentation would be helpful to you. Personally, I've got a few things on my roadmap. The Emacs package is not on Melpa yet. I should do that. It's just like on my own personal repo. It's kind of ridiculous. I want to fix inner tracing so it doesn't blow up so much. And, and a faster Emacs, I want to speed up the Emacs integration. When, as I said, when your trace is pretty big, getting all that information over to Emacs can sometimes be prohibitively slow. I time out every day, and I want to see if there's a way to improve that. All right, so that is the end. I hope that I've convinced anybody to try this thing out, and I hope you enjoy the rest of the conference.